Welcome and good afternoon to everyone. For more than a decade, EPA's Office of Research and Development has recognized the growing importance of wildland fires and has invested limited available resources to expand scientific knowledge, specifically to improve our understanding of the impact of smoke on public health. EPA's Air, Climate, and Energy Program invests in a broad range of research, everything from improving methods to measure individual air pollutants to large interdisciplinary efforts to enhance our understanding of the impacts of energy production and use on our air, our water, and our climate. ORD's Wildfire Advancing Science Partnerships for Indoor Reductions of Smoke Exposures, or ASPIRE study, was started in 2019 as one of our pilot solutions-driven research projects supported by the ACE program. These projects are focused on working with stakeholders to produce integrated research that directly informs solutions to critical environmental challenges. Wildfire ASPIRE is collaborative research with Missoula Public Health in Montana and the Hoopa Valley Tribe in California. We partnered with these local and tribal organizations to target wildfire smoke research efforts to address the immediate needs faced by communities. One of the needs that emerged was to find better ways to help people get cleaner air indoors in their homes when wildfire smoke arrives. The ASPIRE study has been incredibly productive and included a number of different research activities, including field studies, laboratory testing, collaborative partnerships with organizations in Missoula, Montana, and the Hoopa Valley Tribe in California, a collaboration with ASHRAE, the Association for HVAC Professionals, and an open source prize-based challenge. A prize-based challenge is an open competition that seeks to engage a broad community of innovators to solve a particular problem or challenge. EPA has conducted challenges to help solve a wide array of environmental problems, from reducing nutrient pollution in rivers and lakes to finding ways to destroy environmental contaminants. Today's webinar focuses on the Cleaner Indoor Air During Wildfires Challenge. This particular challenge was initiated from our collaborative ASPIRE research study with Missoula Public Health and the Hoopa Valley Tribe. In addition to Missoula Public Health and Hoopa Valley Tribe, EPA partnered with 8 other federal, state, and local agencies on this challenge for a total of 10 partners. The expertise from these organizations was invaluable to inform the scope and design of the challenge and provide input on the solutions we received in response to the challenge. You will hear from one of our partners during today's webinar. So now let me turn it over to Sarah Cofield, one of our key partners for our ASPIRE study, to give you a bit more background on EPA research related to wildland fires, the Cleaner Indoor Air During Wildfires Challenge, and our review process, and she will introduce the Phase 2 winners for the challenge and one of our challenge partners.
All right, thank you, Brian. And welcome everyone to the announcement of the winners of the Cleaner Indoor Air During Wildfires Challenge. It's taken a lot of talented people and a few years to get to this point, and we're so thrilled to be making this announcement today. The challenge came about as part of EPA's work to improve our understanding of air pollutant exposures and public health protections during wildfires. During smoke events, air pollutant concentrations can be greatly elevated, especially fine particles or PM2.5. And the typical public health message during a smoke event is to go inside. But wildfire smoke can infiltrate indoors, which reduces our ability to avoid exposure unless we take action to clean the indoor air. Next slide, please. For today's webinar, I'll provide a brief background and highlights of recent EPA wildfire smoke research activities, followed by an introduction to the Wildfire ASPIRE study, which Brian introduced, and it actually led to the creation of this challenge. And then I will introduce the winners for our science-based challenge. Next slide, please. Wildland fire smoke is a global public health issue, and the magnitude and frequency of wildland fires are worsening. Some areas are impacted by multiple fires at the same time, and many U.S. communities are exposed to smoke for days, weeks, or even months at a time. We've also witnessed over the last few years and last summer that wildland fire smoke is not just a local issue, but a national one, both through the transfer of smoke across the U.S. and also across countries. And based on our 2020 National Emissions Inventory, emissions from fire, which includes wildfire, prescribed are the biggest contributors to primary PM2.5 emissions. And we know that land management agencies, including the Forest Service and Department of the Interior, are working to increase prescribed fire on the landscape to hopefully reduce catastrophic wildfire. So we expect to see contributions from prescribed fire to increase in the coming years. Next slide. Smoke from wildland fires can lead to substantial impacts on air quality and public health. Following slides provide highlights of a few wildland fire smoke research activities led by EPA scientists and engineers. EPA's key wildland fire smoke research topics include better understanding wildland fire smoke emissions, characterizing air quality impacts, better understanding health and ecosystem impacts, and working to improve risk communication and interventions to reduce smoke exposure. Next slide. EPA and our partners have been involved in various activities to better measure and improve our understanding of smoke emissions and air quality impacts. This has included working with emerging technologies to support the use of unmanned aerial system measurements in smoke plumes and testing the performance characteristics of sensors and regulatory monitors during smoke episodes. Next slide. Additional emissions work include gaining a better understanding of wildland fire emissions through controlled burn experiments under different combustion conditions. This allows for more accurate exposure assessments and an improved understanding of wildland fire contributions to ambient PM2.5. EPA has also conducted work to gain a better understanding of multi-year fire activity and emissions inventory data as part of EPA's Air Quality Time Series, or EQUATES project, to help inform air quality management strategies. Next slide. Regarding characterizing air quality impacts, the spatial coverage of PM2.5 monitors has led to challenges in communicating air quality during smoke events. Traditionally, the communication of air quality conditions to the public through the Air Quality Index, or AQI, relied solely on data from regulatory monitors, which tend to be sited in urban areas, which is not necessarily where the smoke tends to be. To increase the spatial coverage of monitors, EPA, in collaboration with the U.S. Forest Service, developed the Fire and Smoke Map, which incorporates data from purple air sensors with regulatory monitor data. And this improves our ability to communicate air quality conditions during smoke events. And while useful, purple air sensors are not as accurate as regulatory monitors. So already researchers developed a correction factor that allowed for the use of data from purple air sensors in the Fire and Smoke Map. Next slide. Another recent effort to expand air quality monitoring capabilities during smoke events is Already's Wildfire Smoke Air Monitoring Response Technology, or WSMART program. This is an air monitor loan program to support it. Oh, can you go back? There we go. Thank you. All right. Sorry. This is an air monitor loan program to supplement existing monitoring by state, local, and tribal air organizations. The program was initiated in 2021 in support of White House and EPA administrator goals and is continued as part of Already's Air, Climate, and Energy National Research Program. Okay, next slide now. EPA has also published numerous peer-reviewed publications examining the relationship between smoke and health effects. This includes animal toxicological studies focusing on different types of exposure durations and conditions, such as different fuel types and combustion phases, and epidemiological studies aimed at better understanding the relationship between smoke exposure and health. The figure at the top right shows toxicological impacts of different fuel types under smoldering versus flaming burn conditions. The second example is what we refer to as the CAPE report, or Comparative Assessment of the Impacts of Prescribed Fire versus Wildfire, and represents work we've done that spans the intersection of air quality and health. The CAPE report is an interagency assessment that was led by EPA and consisted of more than 50 scientific staff from EPA, the Forest Service, Department of Interior, and NIST. The scientists examined the air quality and public health impacts of prescribed fire and wildfire, focusing on 2 case studies conducted in Oregon and California. The report shows on an individual wildfire basis, prescribed fire can reduce the size and intensity of a future wildfire, but prescribed fire also results in air quality and public health impacts. Because of the focus being on 2 case study areas, the results of this assessment are specific to both those areas, cannot be extrapolated to the regional or national scale. Next slide. To support research into wildland fire smoke risk communication and interventions to reduce exposure, EPA recently awarded START grants to researchers across the country. The results from these studies will help inform the creation of effective risk communication and intervention best practices. Next slide. And EPA currently provides resources online for public health outreach and preparedness, including continuing medical education courses about particle pollution and wildfire smoke for medical professionals. Next slide. This brings us to the Wildfires Fire Study. The Wildfires Fire Study is part of an initiative that emphasizes working directly with stakeholders to develop solutions to public health and environmental concerns. EPA started by asking stakeholders what wildland fire smoke questions were going unanswered, and partners, which included myself, as an air quality specialist at Missoula Public Health in Montana at the time, identified the fact that current public health guidance advises going indoors and closing windows and doors during smoke events, but we have little knowledge of how much smoke is still coming inside, particularly in larger commercial and public spaces where HVAC systems draw outside air indoors. Additional questions for the project focus on identifying interventions that are effective for reducing indoor smoke exposures and related risks. The research has involved local partners from the beginning to identify what information they need to effectively communicate actions that building owners and the public can take to reduce public health risks during smoke episodes, and partners frequently to discuss plans, coordinate implementation, address needs and concerns, and discuss what deliverables would be beneficial. EPA worked with Missoula Public Health, the Hoopa Valley Tribal EPA, and the Central California Environmental Justice Network. Next slide, please. The Aspire study has had multiple components. We started with a web-based summit that gathered federal, state, local, and tribal experts to quickly understand the state of science and work currently underway related to indoor air quality during smoke events. The webinar took place in 2019 and is available online. We then conducted field studies in Missoula, Montana, and Hoopa, California, to monitor indoor and outdoor PM2.5 concentrations in commercial and public buildings. This was followed by inspections by an HVAC expert to understand how building characteristics, ventilation systems, or occupant practices affect PM2.5 concentrations. We've conducted laboratory studies to assess DIY air cleaners, and a newer project, Aspire Health, kicked off to evaluate DIY air cleaners' impacts on indoor air quality and human health in homes in Hoopa and Tulare, California. And we just wrapped up fieldwork on that study last fall. And this brings us to the prize-based challenge, which is why we're all here today. We launched this challenge to spur the development of low-cost, sustainable methods to reduce outdoor pollutants in homes during wildfire smoke or high pollution episodes. Next slide. Current air cleaning technologies have limitations that could be addressed through a price-based challenge, including cost, performance, operation and maintenance requirements, noise levels, or reliance on power and a lack of air cooling. So EPA partnered with 10 federal, state, tribal, and local organizations to spur the development of new approaches or technologies to keep indoor air as clean as possible during periods when outdoor PM2.5 concentrations are elevated. Next slide. The challenge was issued in 2 phases and focused on several specific criteria, ranging from price to noise levels, but the most important was the ability to remove PM2.5 during smoke and high pollution episodes. Phase 1 was a theoretical challenge, that is a design challenge requiring an in-depth written proposal, but not requiring development of a prototype. We announced the Phase 1 winners in 2021. We then invited the 5 Phase 1 winners and 3 honorable mention awardees to submit prototypes for evaluation in Phase 2. Next slide. The solvers participating in Phase 2 supply the prototypes to EPA, and they progressed through a series of qualitative and quantitative tests. First, they were evaluated for disqualifications, including potential electrical, mechanical, or chemical hazards, and ozone generation at or above 50 parts per billion. Disqualified prototypes were not evaluated any further. Prototypes that did not demonstrate hazards or ozone generation above 50 parts per billion were evaluated for the must-have and desirable criteria. Next slide. This table shows you the must-have and desirable criteria. The challenge partners identified PM2.5 reduction, costs, noise, and ease of use as the most important characteristics. For additional desirable criteria, cooling was the highest priority, since many areas impacted by wildland fires have a large number of homes without central air conditioning, and elevated temperatures are associated with health impacts. The judge's scoring sheet also included an opportunity to add comments or justification for scoring. Next slide. EPA scientists evaluated the must-have and desirable criteria for each prototype. Pollutant removal was tested in a small chamber, and airflows, noise levels, and air cleaner temperatures were measured in a typical indoor environment, and we had a non-technical user assess the ease of prototype installation and use. Next slide. We summarized the results of the evaluations and provided them to the Phase 2 judging panel. The panel included indoor air quality experts, a product engineer, and public health, communications, and risk experts for federal, state, and local agencies, academia, and the private sector. Once judging was complete, we discussed those results with the challenge partners who helped design the challenge. Input from the judging panel and our challenge partners informed EPA's award decisions. Next slide. Before we introduce our winners, We'll hear some thoughts from Jeff Williams from the California Air Resources Board. Jeff participated in the challenge as both a challenge partner and a judge. Jeff?
Great, thanks, Sarah. So I'd like to first thank EPA for organizing the challenge and the opportunity to be a partner in the development and judging process. It was really a pleasure working with the many challenge partners who helped in the effort and who lent their time and expertise to the evaluation of the submissions. I'd also like to thank the solvers who participated in this important challenge for all their time and effort. So I got involved with the Wildfire Smoke Challenge when EPA staff reached out to me and other challenge partners for a great brainstorming session to develop the objectives of the challenge. I was personally interested in participating in the challenge because I live in California and I've experienced firsthand the serious wildfire smoke episodes that are affecting us all with greater frequency and intensity. The smoke from these fires is a significant health concern for affected communities, and so the need for effective and affordable air cleaning solutions has become increasingly important. And we know that some people may not have access to air cleaners during a wildfire smoke event, and some may have difficulty affording a commercial air cleaner. Also, some people may not have the time or resources to make a DIY air cleaner. So the criteria of the challenge were to develop to the basic need for reducing our exposure to particulate matter during wildfire smoke episodes, and hopefully provide a simple and inexpensive solution that people can use in their homes. Now, I've never participated in a challenge grant, so this was a new process for me, and I was delighted to participate as a judge for the challenge. And as I recall, I think there were about 60 solutions submitted, and I think 45 were qualified ultimately for review. And just a shout out to Gail, Beth, Heidi, Amara, Emily, Sarah, all the other EPA staff that did a tremendous amount of work recruiting partners, holding regular meetings, keeping the partners informed, developing the scoring criteria, holding webinars, and on and on. And all of that work made the evaluation and the scoring of the solutions a very smooth process. We had a wide range of subject matter experts on the judging panels, all of whom were very generous with their time and who made really valuable contributions to the evaluation process. I was particularly impressed with just how similarly many of our judges scored the various solutions, even though we didn't communicate our findings before our group meeting. I'd also like to thank Emma Holder and her team for the excellent technical evaluations of the solutions that advanced to the second phase of the challenge. The judges were provided with a great narrative description of the device, as well as performance characteristics like the clean air delivery rates, power usage, ozone emissions, as well as performance characteristics like the clean air, oh, I'm sorry, and also general evaluation of how easy it was to use the device. And so without this detailed and very practical analysis, it would not have been possible to properly evaluate the devices. So, again, I very much appreciate being able to participate in this important challenge. And I'd again like to extend my congratulations to the Phase 2 winners. And back to you guys.
All right, thank you, Jeff. And again, thank you so much for your work on this challenge.
Thank you.
All right, and now it's our first winner, Dr. Elliot Gall for the Cocoon. Dr. Gall, can you advance slide, please? There we go. Sorry about that. Dr. Gall is the David Wedge Vision Associate Professor at Portland State University, Mechanical and Materials Engineering. At PSU, Dr. Gall leads the Healthy Buildings Research Laboratory, where he and his research team conduct fundamental and applied research exploring the many factors that impact our exposure to air pollution inside buildings. Dr. Gall?
Okay, thank you very much. Next slide, please. I want to start by saying thank you to the US EPA and the challenge partners who hosted this really important design competition. I think this was a unique and creative way to spur innovation in a space that's much needed. It's already been stated how important air cleaning is during wildfire smoke events. And this is a topic that's of focus for my research lab here at Portland State University, which I call the Healthy Buildings Research Lab. You can find out a little bit more by following the QR code down in the bottom left there. Our submission to this challenge we call the Cocoon, which is intended to be an accessible and extremely low cost and ideally no cost air cleaner to create a safer space during wildfires. And just to cut right to the solution that we came up with, you can see some photos of some iterations of the design on the left here. Our approach is to create a very simple, very low cost, do-it-yourself air cleaner that consists of a fan. We used a box fan, but we're thinking any air movement device could potentially be used for this solution. A filter that can be made from materials that are available offhand, household materials. In this case, we use cotton fabric, and some method of securing that fabric to the fan. And the results of this effort are an air cleaner that, at least initially, we were pleased but also surprised that is effective. It meets the challenge criteria for removing PM 2.5 from a space. Even if you purchase every component new, it's less than $60 or so. But again, our intention here is to try to come up with guidance that allows people to create free air cleaners using materials that are readily available in many households already. And to boot, our hope is that the filtration material, by leveraging fabrics, can be reusable. So a sustainable, low cost, easy to store material that can be used as an air cleaning device during emergency circumstances. Next slide, please. So everybody likes analogies. Think back to the old school SAT here. I want to frame the context of our thinking for this solution with an analogy. So there's a couple of animations here. So go ahead and just click through. 4 pictures should appear. A cloth face mask is akin to an N95 face mask, as the cocoon is akin to an advanced 3-stage HEPA filter. So as an indoor air quality scientist, at the advent of the phase 1 of the challenge, cloth face masks were a hot topic in my field of indoor air quality. A lot of questions, a lot of active research on this idea of using a cloth face mask to protect yourself and others from virus-containing aerosols. Obviously, that's a different solution than a highly engineered product like an N95 face mask. What came out of some of the research that went on in the indoor air community about cloth face masks is people did find that fabrics that are commonly available can remove particulate matter. So that research is out there. I'm not here to talk more about that, but that thinking informed the initial inspiration and design of this device. When this challenge came out, it seemed like a nice parallel to say, if people are finding out these cloth face masks can filter some fraction, not 95%, not 99%, but some fraction, can we leverage that same idea and create, again, an accessible, very low-cost air cleaner that serves a different niche than something like a 3-stage HEPA air cleaner that's highly engineered, constructed, in a factory to specific tolerances, so on and so forth. We're looking to meet an emergency need with materials that people might even have on hand already. Okay, next slide, please. So this is a graphic that Portland State University, I want to give credit to them. Their graphic designers did a nice job illustrating one iteration of our design here at the end of the phase 1 challenge. And so we've worked through a number of iterations, and all of them can be effective, but the one that we've studied the most extensively in my lab and had submitted to the EPA as part of this challenge involves a box fan, a ratchet strap to attach a sock-like fabric material that we sewed into sort of like a windsock material that's affixed to the outlet of the fan. So it acts very simply like a filter, a relatively low efficiency filter, but box fans move a lot of air, and we can recycle air through that filter many, many times and actually realize a decent overall effectiveness from this very simple solution. We're working through other design iterations. It actually turns out that you can affix that filter to the box fan a lot of different ways. That part is relatively less important than this idea of getting an air moving device with some large surface area fabric material. We've tested cotton, and that's performed, at least so far, the most efficient. So get air moving through that cotton, and we can realize some air cleaning effect, which I'll show on the next slide, please. So when we had the sort of origin of this idea, our first thought, and some students helped with field testing, was this was a little bit of a wild idea, and we thought, let's try this and get right out to the source. Let's go in the field, use this in a manner in which someone might, during an actual wildfire smoke event. So this is one of my students' bedrooms who tested this device in their space, mimicking a wildfire smoke event. So what you see on the right there is a plot showing us injecting wildfire smoke and it being removed from the space with and without an air cleaner running. So you see in blue is when the air cleaner, the cocoon, is running. The red is when it's not. So you see a much steeper slope. We're removing particulate matter from that space. If you go ahead and advance to the next slide, or click next, we'll see, yeah, highlighting that peak is when we're injecting, and then the fall off is the air cleaner removing PM 2.5 from that space at a more rapid rate than what's happening in the background. So this was sort of our first inkling that, hey, we might be onto something here. And when we ran the calcs, we showed that, we're in the ballpark here of what the EPA is looking for. And so fortunately, I run a research lab and we're able to probe this in greater depth and with more control. So then we followed this up with lab testing. And, I don't have time to go into the details here. If you advance one more, you'll see the next animation. We were able to test under controlled, repeatable conditions and probe this a little bit further and confirm and just really be confident what we think we saw in the field is happening in a controlled laboratory chamber. We're able to show that. And we're able to, the short version is see results for clean air delivery rates, essentially the volumetric flow rate of cleaned air that's coming out of that constructed air cleaner is in the ballpark of what the EPA tested. So we have general agreement with what the EPA is finding. So this is a do-it-yourself, very low cost, ideally no cost air cleaner that would be appropriate for a small room, something like the EPA recommends for use in a clean room where you find perhaps a bedroom or small volume space in your home. Set up even something like this low cost, do-it-yourself cocoon air cleaner, and you can substantially and meaningfully reduce PM 2.5 concentrations in that space. Even if it's not the perfect, most highly engineered, top performing air cleaner on the market, you might be able to make one from things you already have in your home. Next slide, please. Okay, so what's next? Again, I'm thrilled and honestly humbled and very thankful for the EPA for hosting this competition and being selected as a phase 2 winner. We have some plans for the prize funding here, and we're going to continue on this work. And again, I'm really appreciative of this because it can be difficult to fund this sort of practical, innovative work via other mechanisms, at least in academia. So we want to test other household fabrics and look at different ways of constructing these devices. I think most households have fabrics, have fans. We want to come up with guidance that, again, allows people to do this using the things they already have. And so part of that is working with community partners to come up with ways of disseminating how-tos and information in ways that reach the people who might benefit the most from this. One question we get a lot is, can you wash the fabric and how does it perform? We're going to study that. We haven't looked at it with the specific filters that we've studied, but again, in the context of cloth face masks, people have looked at that and shown that you can wash fabric and maintain removal efficiency. So we have a strong feeling that we will be able to wash these and reuse them following a smoke event. Again, a nice differentiation from the standard filter that needs to be thrown out. Nice part about being in Portland, Oregon is we have a lot of outdoor apparel companies here. We want to try and work with those companies to come up with some solutions that might be scalable and very low cost. So, get these filters produced at, scale that we might be able to disseminate them in advance of the summer wildfire season. And finally, I think there are other emergency scenarios. Again, the idea here is, can you MacGyver something as needed if an emergency arises? So are there other instances where we might want emergency particle filtration in people's homes? One example might be, release of tear gas in an urban environment, for example. That's a particle that could be filtered out from an indoor space. We want to explore other uses for this solution that we contrived here. So I really want to thank the team. This has been such a fun project working with great students. You already saw Brett Stinson's photo. He did much of the testing. This was a unique example. I was able to work with my mother-in-law and father-in-law, Kathy Ryan, sewed and helped me brainstorm and think through the initial sort of construction of that fabric filter, iterated upon by Michaela Reed, who did a nice job sort of iterating a unique a band that allowed it to affix to a box fan. Matthew Moore and Warren Gunn helped with field studies and other parts of the iteration. So that's all I have. Happy to answer questions during Q&A. And again, thank you to EPA and its challenge partners. And we're really grateful for this challenge. So thank you.
Wonderful. Thank you so much, Elliot. Go ahead and advance to the next slide, please. All right, next we have Cece Liu with Metalmark Innovations. Cece is passionate about solving complex societal problems with cutting-edge technology. She has 20 years of experience in climate tech and sustainability, entrepreneurship, and venture investing. Cece co-founded Metalmark Innovations, where she is CEO to tackle the global air pollution crisis and climate change challenges. Cece holds a BA from Wellesley College and a master's from Harvard University. Cece?
Thank you, Sarah. We go to the next slide, please. Yeah, so thanks again for this challenge. We're so thrilled to receive the award. My name is Cece Liu, CEO and co-founder of Metalmark Innovations. We're the inventor of the world's first self-renewing air cleaner. So last May, headlines of wildfires and smoke activity started to top the news. At the time, smoke maps already showed a broad geographic coverage of poor air quality across the US and Canada. And the situation worsened by June when cities like New York were blanketed and became some of the most polluted cities in the world. And that included where I live in the Boston area. And so despite the efforts by the US led by agencies such as the EPA to reduce air pollution, climate change is creating more challenges than ever before. And according to the American Lung Association, more than a third of Americans currently live with poor ambient air quality. So this means to us that we must start adapting to the changing climate and making our buildings more resilient and in a sustainable manner. Next slide, please. At Metalmark, we started our technology development by first trying to understand wildfire smoke. And it turned out that the science around it was still an understudied area when we first began. We recently published a peer-reviewed paper on the subject of wildfire smoke and filtration, and the link is provided on the slide for anyone interested in learning more about it. And what we found through our literature research and testing is that smoke particles are sub-micron in size. And this is shown in the chart to the left. The largest of PM 2.5 particles are 30 times smaller than the diameter of a single hair. At less than 300 nanometers, smoke particles are about 300 times smaller than a hair. And the closer you are to the fire source, the smaller the particles. But even at locations thousands of miles away from the fire source, such as away from Canada last year in Boston, or traveling to Greece, where recent studies have shown the smoke particles still remain below 500 nanometers. And what makes the particles particularly problematic and a major health risk are their diverse chemical components and their dynamic transformations. And it's been associated with increased hospital admissions, cardiovascular and respiratory diseases, mental disorders, and such. It has also been shown to increase fungal infections such as valley fever. And so it's a really concerning development that we all have to start paying more attention to. And we're very grateful for the EPA to have taken the lead on this. But what's interesting also is I want to point out that particles in our indoor environment, our homes, offices, and schools, share some characteristics with smoke. Indoor particles are vastly smaller than 500 nanometers in size as well. And this is revealed when we looked at particles from the size resolved count perspective, and that's shown in the diagram to the right. Next slide, please. One of the common recommendations for protecting ourselves against wildfire smoke is to upgrade to MERV 13 filters in the HVAC system. In our research, we conducted filtration tests with pine needle smoke to understand its interactions with filter media, which is one of the most important drivers for HVAC filter efficiency. So in your homes and offices, this is one of the biggest elements for how efficiently your system can filter out smoke. And as you can see in the scanning electrons microscopy image to the right, smoke accumulates on filter fiber like pearl strands. And this is very, very different from what happens with salt accumulation that I bring that up because that's how filters are typically tested under standard testing methods. And the differences in material behavior has a lot of implications for filtration efficiency. And so we found that typically when we go out to buy filters, we depend on the MERV rating. And MERV ratings of filters were developed for general applications. So when it comes to smoke, it appears to not actually represent an adequate picture. The higher grade MERV filter media made with charged polymer media have a lower efficiency for smoke removal than suggested by their ratings. Whereas a similar grade mechanical media are much better for smoke removal, but this also depends on the manufacturer. The other downside of typical mechanical filter media of MERV 13, 14, 15 grades is that they tend to have very high pressure drop, and that has, again, implications for your HVAC system when it comes to energy use and also potential lifetime of the equipment. So the recommendation to filtrate with MERV 13 filters have to be further studied and examined is one of our main conclusions. Next slide, please. Aside from filtering with HVAC filters during smoke events, another standard recommendation is to run an air cleaner. And shown here are the two prototypes that Metalmark entered to the EPA's Cleaner Indoor Air during Wildfire Challenge. In our innovative design, we targeted high smoke removal efficiency and solving for the perennial problems of height maintenance, filter cost, and waste creation. And the system that we built self-renews the onboard filter, which is coated with our proprietary butterfly-inspired material. And that's why, you know, the Metalmark logo is shaped like a butterfly. Under normal usage, the filter could last up to 5 years. Next slide, please. Since our submission to the challenge, we received the patent for our unique air cleaner, and we rely on the same technology concepts to design the Tatama, which targets commercial building applications, whereas the challenge was geared towards residential use. And so in this, in the Tatama, we were looking to balance the needs for better indoor air quality and building energy use. Next slide, please. Each Tatama covers about 1,000 square feet with up to 3 air changes per hour, and it's ideally suited for schools, offices, medical facilities, and more. Next slide, please. The Tatama's patented technology includes a 2-staged process. And again, this is exactly what we did in the EPA challenge as well. In the stage 1, direct air filtration removes indoor pollutants. Based on third-party testing according to AHAM standards, our system achieves 350 to 360 CFMs of virus, bacteria, and smoke clean air delivery rates, CAGR. And we're working to further improve that. If you can click next, please. And in stage 2, around just once per month, the system self-renews the filter. Particles trapped are decomposed so that the filter's pressure drop is partially recovered. The catalysts on board break down gases formed during the process to prevent any harmful byproduct release. Next slide, please. Sorry. The Tatama is ceiling mounted and self-ducted to achieve optimal air cleaning flow regime and avoid introducing appliances that take up room on the floor or walls. So it's really ideally suited for retrofits, especially in older buildings with limited options for HVAC upgrades, but it's also equally designed to suit new builds and for architectural installations. Next slide, please. This smart, distributed, and targeted IAQ approach helps to reduce HVAC ventilation energy use, which is one of the biggest drivers for building HVAC energy. It's ultra low maintenance and cost effective. We have environmental sensors built on each unit to gather real-time IAQ data to provide customers with insights through our apps. The data also enables smart operations across the network of units at a building and campus scale. Our systems have been customer installed at multiple sites, and we're very excited to introduce it to market. Next slide, please. Metalmark is a women-led public benefit corporation that spun out of Harvard University. And I want to take this opportunity to thank our core project team and our engineering consultants at Alogis, and many of our partners, funders, and supporters such as the NSF, NIH, and the EPA for making our progress possible. Next slide, please. So if you have any questions, please contact us by email, or I can take questions during the Q&A session. And that concludes my presentation. Sarah?
All right, thank you. We're going to hand it over to Emily Snyder right now, who will moderate our Q&A. Emily?
Good afternoon. The first question we have is for Elliot. So the questioner asked, could you use an already owned cotton or nylon laundry bag instead of a custom-made fabric filter?
Yeah, that's a good question, and I think that's something we're going to keep looking into. We haven't studied nylon, so I'm not sure about that. Cotton, I think, has sort of a fibrous matrix that seems to be conducive to filtration. So, my inkling or my suspicion is that would probably be a better place to start. But as far as how aging or used materials might work, I think that's a topic that we're going to look into using this award to try and answer that question, and also try and collect some household materials that people might donate to us that might be able to be easily adapted into a filter to test those sorts of questions. I think that's sort of where we're at, is how specific, how flexible can we be in modifying that filter to kind of use what's offhand versus what are the benefits of trying to design something to basic specifications using things that people already have. That's sort of open right now.
Thank you, Elliot. The next question is for Sissy. Great work to develop this. Congratulations. It looks excellent. How does the efficiency for the PM 2.5 compare with a HEPA filter? And what is the approximate cost of the device? And when do you think we can get one?
So the Tatama is currently being prepared for market release, and it is the efficiency is comparable to HEPA air purifiers, because we start with our filter is HEPA grade. It has the embodiment of our novel material that I mentioned, which is a nanostructure butterfly inspired material. Yeah, the system is designed for commercial building use and typically at the building scale. So we typically work directly with our customers and can definitely work to quote and make sure that we get bundle discounts for any larger customers interested.
Thank you. Cece, could I ask you just another follow-on question? What is the weight of the Tatama unit?
So the Tatama is currently about 70 pounds. We are working to get that weight even lower.
Awesome.
We actually today just had some installations, and it was really remarkable to see how easy it was to go in the ceiling.
Thank you. All right, this next question is for Elliot. For some fabric filters, you see an increase in efficiency after the fabric has been used for a while, after it's a bit dirty.
Yep.
Do you anticipate something like this happening? Will there be a method to evaluate the optimum times that washing should happen?
Yeah, that's a great question. I just dropped a quick answer in the chat, but I think it's worth mentioning that I do expect that there will be a change in removal efficiency. I think that's sort of, in line with established filtration theory. I think there's likely a trade-off. So we have done experiments on different fabrics that all had sort of, different levels of, permeability, airflow permeability, sort of as a virtue of their design. And, we measured the airflow through the box fan with these different materials attached, and we did see meaningful differences in airflow. So while I do think loading will change filtration efficiency, that's one part of the equation. The other part is, are you still able to move air through that filter? And I think that's sort of one of our higher priority research questions to try and evaluate is, do we see that bump in removal efficiency as the filter loads, which you'd expect? What's the trade-off for a box fan, which is not designed to overcome high pressure drops in terms of the airflow being moved through that air cleaner? So it's a great research question, and I'm thrilled that we now have some resources to continue studying that.
Great, thank you. So this question is for both Cece and Elliot. So Cece, if you want to go first, has either product been evaluated during an actual wildfire event?
So our unit has not gone into an actual wildfire smoke event. What we have done is primarily do third-party laboratory testing with both cigarette smoke and pine needle smoke testing in large size chambers that are much more representative of how our system would perform in the field. We have had other pilots with customers, as I mentioned, and in customer installations where we track the efficacy of our system for a number of pollutants, including PM2.5, VOCs, bacteria, and mold. We showed reduction of all of those. So the answer, I guess, is we haven't done it in in the field for wildfire smoke, but we try to be as comprehensive with our testing for the finer PM2.5 as much as possible.
Thank you.
Yeah, so on our end, the short answer is no. I mean, we study wildfire smoke as a major area of research, and it puts you in a very awkward position of needing or wanting wildfire smoke to advance your research objectives, but desperately not wanting wildfire smoke for every other aspect of your life. So we have been out in the field, and we have done tests where we simulate that effect with, fresh biomass being combusted, injecting smoke into the environment. So we are mimicking the process. We are testing it we have tested it in a real environment, not with what would constitute a true, likely more aged wildfire smoke event. We've done that for other DIY air cleaners, just haven't had the things line up for the cocoon. But this summer we're aiming to do that.
Great, thank you. So Elliot, I'll ask you another question while I have you. Is there a filter at the far end of the cocoon, or does the filtration rely only on the sides of the cocoon?
Well, so far what we've looked at is a standard 20-inch by 20-inch box fan. And, you think of like a sock being sort of fit over the box fan. So the box fan pushes air through, what we've tested is anywhere from like 2 to 5 foot long, like sock of fabric. So I hope that answers the question. I don't really know what they mean by the sides. But that entire surface area of fabric is acting like the filter, which is one of the reasons why the device is able to be efficient. With fabric, you can have as much filtration as you want, really. So you have a lot of surface area for that process to happen, low pressure drop for the fan. So that's where the filter is located, is all throughout that large length of fabric attached to the outlet side of the fan is what we've tested.
Great, thank you. So one more question for Elliot. Have you evaluated your design for smaller PM particles?
Yeah, that's a good question. I didn't have time to go into it. The last plot I showed in my lab, I think someone else asked this, so it sort of answers that, is what are we using to measure PM2.5? In the field, we've used lower cost devices, Purple Airs and Dylos particle counters. In my lab, we have the ability to measure from 10 nanometers to 10 micrometers. And in the plot I showed, we were able to size resolve those clean air delivery rates. So we did measure it, and in what I showed, it's lumped into 3 bins, less than 0.3 micron, 0.3 to 1, and 1 to 2.5. So all in the PM2.5 range. But there is a difference, right? And so the smallest CADR we saw was in that sort of 0.3 micron range, which is typically the most penetrating size, sort of hardest to remove generally. And that's where a lot of wildfire smoke is present, as Cece's plot showed us. Generally, when you get much smaller and much bigger, your device tends to be a little bit more efficient for the kinds of filters like a piece of fabric might act like. So, if there's a challenge aerosol with a bunch of really large particles or a bunch of really small particles, we might actually see better CADRs than the one I highlighted at the end of my talk there.
Thank you. So this next question is for both Cece and Elliot. So Cece, I'll start with you. Have these systems been evaluated for gases and aerosols? High concentrations of reactive gases can produce particles when run through traditional HEPA filters.
So our system, the Tatama, has been evaluated for with aerosols and with smoke. We did not test specifically for certain VOC removal. However, there are many VOCs that are carried in smoke, in cigarette and wildfire type of smoke, and we do show reduction of those. And aerosols of virus and bacteria we have tested as examples.
Yeah, and for our
Elliot.
part, we have actually tested our devices for gas phase removal. In my lab, we have what's called a proton transfer reaction time of flight mass spectrometer. So it's a mouthful, but it lets us measure organic compounds in real time. We didn't really expect to see organic compound removal or meaningful organic compound removal from our cotton fabrics, but it is intriguing. I've seen some data to show that wool type materials might be selective for certain oxygenated organics. So that's something that I think will be a very interesting research project, but perhaps secondary to the goal of trying to optimize for particulate matter removal. But we do have that capability and are planning to try and work in those sorts of studies as part of our next steps with this award.
And the next question I have is for both of you as well. So Cece, I'll start with you. Do you think there will be any differences in filter efficiency with prescribed fire smoke rather than wildfire smoke?
There are definitely differences. So the smoke composition is dependent on the source and the type of combustion and the conditions of combustion. So it's very hard to say definitively how different they are at this moment. I didn't look into it. However, from a filtration efficiency perspective, those I expect that the efficiency should be similar for our system in terms of removal, PM removal.
Elliot?
I'm sorry, I was answering questions in the chat. Can you repeat the question?
Sure. Do you think there will be any differences in filter efficiency with prescribed fire smoke rather than wildfire smoke?
That's a good question. Wildfires, especially at like the wildland urban interface, I suspect might be burning very different kinds of materials that likely produce different, a different wildfire smoke mixture essentially. So I suspect there could be. I think the aging effects that occur during long range transport might have an effect too. If, for example, our testing with very fresh, biomass smoke that we've combusted ourselves likely is different than something that's been transported for hours or even days, regionally. So I think there are some important differences there, and that's where I think measuring size is a major determinant of removal efficiency through filtration. So that's where it's important to have some measurement of the size distribution of your challenge aerosol and how your air cleaner responds as a function of size. You can get at some of that, maybe not all of it, but a good portion of it.
Thank you. All right. And I think this might be our last question. It's for Cece. What is the MER filter used in the Tatama?
So our filter grade is HEPA, and so it's we could also use a MERV 16 filter. So it's really, a lot of it comes down to the material selection and the filter design, and so that's something that we work on as well. It's principally a HEPA grade filter.
All right, I think we have time for just one more. So the last question is for Elliot. Have you explored how this compares to a Corsi box filter? And have you spoke with Professor Corsi about it as well?
So yeah, Rich Corsi was one of my PhD advisors. So shout out to Rich Corsi, because the work that he and Jim Rosenthal did, inform what we were trying to do here. We have tested CR boxes extensively in my lab for other reasons, and they perform to a better specification. They have a higher performance, right? So they're using MERV 13 filters, duct tape. It's a more involved construction process. And I think as a result of that, you get more air cleaning. So that's part of why I wanted to frame the motivation. Really, our goal here is to try and set another tool in people's toolbox of, what can you do for no cost is really the goal here, $0. And then, scaling for benefits in the $0 to $10 or $20 range. Corsi Rosenthal boxes can be quite inexpensive as well, but obviously you have filters to purchase, duct tape to purchase, and some work to do to assemble. So we're trying to go far on that other end of the spectrum. But CR boxes are great, and Rich Corsi is a dear friend and colleague. So if he's here, thanks, Rich, for all you've done for me.
Well, thank you both for answering all of those questions. I'm going to turn it back over to Sarah Cofield to close us out.
All right, thank you so much, Emily, and thank you, Cece and Elliot. I'd like to take this opportunity to thank our judges and partners for their time and effort that went into designing and judging this challenge. Thank you as well to all of our challenge participants who put forward designs and prototypes. And thank you to our EPA staff who completed thorough testing on the prototypes. And finally, thank you all for attending our announcement, and congratulations again to our winners. A reminder, a recording of this webinar will be posted on the Air Climate and Energy Webinar Series webpage, typically within a couple of weeks. So that's what we have for you today. Thank you so much, and congratulations again, Cece and Elliot.